Okay guys, so welcome to Algebra 2 Lesson 3, solving linear equations, variables on both sides. And I got a little carried away with myself here. This first note in the lesson goals says we're going to be able to write linear equations with a variable on both sides. Then we're going to solve those linear equations with a variable on both sides, be able to check solutions, and justify each step of our process. So, some words to know. Do yourself a favor, pause this video, attempt this little glossary vocabulary exercise, and then come back for the answers. So part A here says, the A definition says, terms that consisting of the same variables raised to the same powers. So like, if it was K and K, 3K and 7K, just because I got more of them, 3K, 7K, they have the same variable, both raised to the first power. Those guys are like terms. B, the rules that allow the balancing, manipulation, and solving of equations. Those are properties of equality. Can't do to one side what I won't do to the other. C, to separate from other substances, to place apart so as to be alone, is to isolate. In this case, we're talking about isolating variables. And D, an algebraic equation which consists with constants and variable terms of the highest degree 1. Those are linear equations. Remember, 1, x1 linear, x2 squared. I mean, it just goes on. We'll get into that later again. Okay, so we're going to talk first about determining specific input values. So scuba diver travel, I can't read today, guys. A scuba diver travels into deeper levels of the ocean. The diver experiences increased pressure. The function, this is pressure per meter, is equal to 1.05 times the meter plus 10 models of the pressure, P, in atmospheres. The diver feels at a depth of m meters. I know it's a lot, but here's your formula, okay? So determine the depth of a diver who experiences 810 atmospheres of pressure. Well, that's the pressure here on this side. So 810 is equal to 1.05 meters plus 10. So of course I'm going to start with this property of equality of subtraction. Move that 10, subtract 10 from both sides. Then I'm going to divide both sides to get 800 divided by 1.05. So I'll get to stick that in a calculator, and we're looking at 761.9 meters approximately. Okay, rounding it to the nearest hundredth would be 90, to the 0.9 would be the 10th. But that's how they find the depth using atmospheric pressure. So to model linear growth, what we're looking at here is if we wanted to know when the two towns would have the same population, we could eyeball the two graphs, okay? So this is their number of residents on the y-axis and the years since 2000 on the x-axis. When do they get equal? A couple of ways to do this is to start here at the bottom with a piece of paper, any piece of paper, and as you slide it straight up that y, you find points that they're equal, like there, those 2 points, at about 6,000. Well, how long is that? About 10 years. So what we're looking at is when we eyeball that, we look at this point here and here as being about equal. And we say that's roughly about 10 years. But what if we wanted to know exactly? What's the difference of knowing roughly and knowing exactly? Okay? So we're going to do the same thing here. We're going to find this to the best of our knowledge. It says population trend for Berthoud County can be represented by this function. And the population trend for Wellington County can be represented by this function, where T is the time in years. So, T. When will they have the same population? What we're trying to do is solve for T here. So I've got this, if they're both equal to the population. When are those populations equal? I could drop that and set this equal to this and solve for T. That's all they have done here. Set those two equations equal to each other. All right, now that we know what we're doing on the writing part of the equation, we start in solving it. So they're going to take all the constants to this side. Okay, and that leaves 106.67 T equal to 308.8 T minus the solution of these two numbers. Then if I move this T over there, I wind up with this. When I subtract it from both sides, it's okay if it makes negative, don't flip out. When I divide both sides by this constant in front of T, I'm going to wind up with T equaling 9.496. So that means that it's going to, we're starting at year 2000. Okay, so 9 years later would be 2009. And somewhere nearly halfway, 0.496 is nearly 0.5. If you round it up, it is. So about halfway between 2009 and 2010, that's when the two towns will have the same population. So working on a linear equation, they have the same essential relationship as a linear function, but the goal is not to represent a relationship, but to find a specific input for which the two functions are equivalent. So we're basically finding that point where if you just graphed the two functions like this, two lines, and here's the second line, we're looking for this point right here that they intersect. That's when they're equivalent. So in order to do this, we combine like terms on either side of the equal sign. It doesn't really matter. And we use the properties of equality to isolate the variable. Then we check our solution by using substitution. So, moving right into a problem. Solving a linear equation. Here's a linear equation. We combine like terms on either side. So here they have this, what I can combine are these two guys, 2x to the fifth minus 5x, and that's where I get this negative 23 over 5. And then while I'm at it, I can go ahead and move this x over here by adding it to both sides. Then I've got this constant that needs to be moved over there, right? What did they... I'm so sorry. Let me start again. They moved this to the other side. This is the result of combining those two x terms. So if I move this, that's 23 over 5x. The x should be out here a little more, so sorry. So I'm adding 23 over 5x to both sides. Now that completely removes it from there. And then I combine this negative x and 23 over 5x, which is really, yeah. And I wind up with 18 over 5x plus this 1/5. So I hadn't done anything with it. So I take that 1/5 from both sides. Well, 12 minus 1/5 is 59 over 5. Then I've got to divide both sides by the reciprocal of 18 over 5, which is 5/8. And when I do this division right here, that cancels, so I'm left with 1x. When I do this division, these guys cancel, cross simplifying, and I wind up with 59 over 18. Now, I want to check that solution. I'm going to check it by using that 59 over 18 to substitute in for x. So I find my original equation, which was, there was an x here, here, and here in my equation. And I put the 59 over 18 into that. Now this can just be punched in your calculator until you get a solution that is the same on both sides. And if this equals this, well, yes, that's true. Thank you. So this is a true answer, a true solution. That is your solution. You checked it there. Okay, we're going to look at solving a linear equation. I'm on the wrong page again. Nope, I'm not on the wrong page, so sorry. Writing and solving a linear equation. Here's a real world connection to this, okay? A limnologist studies the dissolved oxygen levels in Lake Erie. At a depth of 10 meters, the dissolved O2 levels change. See where this is all going? Take a minute and read that until you understand what's going on for each equation. Okay, so the first input is the temperature in degrees Celsius. Here's that amount. So that is negative 0.32x. And then we're looking for this amount for the second, which would be its per degree Celsius rate, dissolved oxygen level, which is this number. At 20 meters, it is 15.05. So we create a linear equation by setting the two functions equal. They're already y equals and y equals. So we just take this part and set it equal to this. When we do that and we solve it, as we go through here, by using properties of addition, equality, the equality property of subtraction, the equality property of division, we wind up with x equaling 9.05, which means that at 9.05 degrees Celsius, the dissolved oxygen at 10 meters is equal to the dissolved oxygen at 20 meters. Okay? So let's back up. When is it got? Where's my other page? So another way, and this is just quick, I'm just going to go through this one quick. But another way to solve a linear equation is multiply by the common denominator of all the fractions, if you want to go through that. Combine like terms at that point. And then isolate properties to solve for x. Key concepts here that you need to look for is in linear equations, find a specific input when two linear functions are equal, and combining like terms on either side of the equal sign. Use properties of equality to isolate variables, and check your solution. Always put your answer back into your problem and see if you get a true solution. Okay, that's it for lesson 3. You should be good on this to finish your assignment and go to the next lesson.